So welcome back. Now we are going into the second part of the lecture, which is on brushing up SQL. So some of you actually might already know SQL, probably a lot of you actually who had a course at the bachelor's level. Actually, I'm going to ask the question. Okay. So tell me how familiar you are with relational databases and SQL. What is this? I've heard of it. I've programmed in SQL, or they have no secrets for me. You will see, I'm pretty sure there will be people who answered with the last answer. Happens every time. Told you. So we have SQL, how do we say, connoisseurs in there. So people who are really, really familiar with SQL, that's really, really great to know. Most of you, as expected, have already used SQL. You were taught SQL in a good old relational database lecture during your bachelor's, probably for many of you by Professor Chang. So you know about select from where, group by, having, and so on. Some of you heard of SQL. That's also really, really nice. And some of you don't know what it is. Don't worry, I'm going to tell you what it is, and we are going to brush it up. So I have to give you a warning about what's coming. Precisely because of this distribution, for some of you, it might be boring or like I already know all of that. Don't worry, just take it as a brush up. We just bringing back to your short-term memory, and then you just bring everything to the front of your mind. For those who never heard of SQL, that's again why I'm giving the warning. I'm going to throw at you today and tomorrow 1 semester worth of SQL material. Do not be scared. SQL is really easy to learn. So even if you don't get all the details, because in a SQL lecture, we do a lot of theory. We study normal forms. We study many, many things in details with the relational algebra. But the reason I'm doing the brush up is not that it's a prerequisite. Don't worry too much about that. What I want you is to learn the SQL language and make sure that you know the SQL language. The SQL language is really not so complicated. It's very intuitive. And in fact, we have an exercise sheet that will be available from next week where you can program in SQL. You will see it's much easier than you think. Just the best way is to just dive into SQL and write a few queries. You will see in the Jupyter notebook, it's beautiful. You have a table and you write your query and you have a nice table as the results that appear, and you can just play with it and learn it. So I really, really encourage you to learn SQL, because SQL will come again during the lecture, when we will start using SQL, not on top of a regular database, relational database, but on top of Spark with Spark SQL, right, for example. So there's many places that SQL is also useful in a cluster of machines, right? So I hope that with this warning, now I can proceed at the risk again of boring some of you and scaring some others, but really, really do not panic. This is really just a brush up lecture. It's not going to be like that every week. This is really special and just for this quick brush up.
My LAN actually dropped out. So can you accept me on
oh, yes.
Zoom, please?
So Fabio was kicked out of that actually happens once in a while. But it provides for entertainment, it keeps things interesting.
Yeah,
does it
and
work
then
again?
make me, I guess,
co-host. Yeah.
Thank you.
I need to find again the Zoom window. Need to stop. Oh yeah, there I am. I'm back. So first, make Fabio a co-host. Here you are. And you are here with the co-host. Now I'm going to share my screen again with the slides. coming right up. Yes, there you go. And it's recording. Perfect. All right. So let's go ahead. I'm going to take things as gently as possible, but there will be a lot of information. Focus on the high level. All right. So first, this person, Edgar Code, he can be considered the father of databases. He's the most important person in the sense that he basically seeded the whole field of databases. We had a brilliant idea, Edgar Code. It's data independence. Data independence means that before, people used to be working directly with files on the hard drive, by the way, just like Python today and so on, just saying that. And it was so complicated that he said, no, this doesn't work. We really need a better system that works on a higher level with tables, and people just think in terms of tables. Everybody understands tables. It's been there for thousands of years. It's super intuitive. What's really cool with data independence is that now that we have a data model that is super simple to understand, we can start changing what's going on there. We can actually change that. Yeah, Clay Tablet works nice. We can change it to some spreadsheet software, whatever, like anything that basically manipulates tables, a single hard drive, on your machine, a cluster of machines, which we'll actually do in this lecture. So you can execute table computations on top of clusters of machines. DNA, as I told you, some people even manage to execute SQL and relational algebra on top of DNA, right? That also works. This is what's cool about data independence, because you see, I can change that. There is one thing that didn't change, and that's this. So if you learn relational tables and SQL, you are basically, you open up a whole realm of possibilities of usage of relational tables and SQL, right? It's super generic. All right, now I'm repeating something I said before, and that's super important. 5 fundamental data shapes: tables, trees, text. You can also put here pictures and all the unstructured data, audio, video, cubes, graphs. 5 fundamental data shapes. We'll see that they are central to everything in our course. We're going to study these 4 in our lecture, but right now the brush up will be on tables. Why? Because these are the oldest. This is again in the 1970s where the focus was. So I'm going to talk to you today and tomorrow specifically about relational tables. So the way this works is that there's a whole stack, a whole architecture, where we have a way to store somewhere the data. In the end, it's just going to be files on a hard drive, right? It's just that the user doesn't see that. It's going to be processed by the CPU. There is the table model. We're going to look a little bit into it. So this is the relational model that tells you where the table is, and then a language to process the model, right? So all the users need to understand is above, my arm right there, everything below, the user can just ignore. This is just taken care of automatically. So in order to define a model, we need to explain what data looks like and what you can do with this. So I like to have a little analogy with cooking, is that when you cook something, what is food? It's something that can be eaten. What you can do with it when you cook, you can mix, pour, break, dry, bake, grill, melt, mince, mix, and so on and so on. Right? So there's a whole set of verbs of what you can do with all the ingredients that you have. So this is the same with the data model. We say what relational data looks like and what you can do with relational data. And what happened then, and the reason why SQL and tables are so important, is that since I told you that everything above my arm is what the user cares about, and everything below is hidden, we can, well, not silently, because of course it's a lot of buzz on social media, but we can swap this for a cluster of machines and keep the upper part with the language and the model. That's the beauty of it. Then we can even swap, and we'll do it in the lecture. Instead of tables, we can use cubes, trees, and so on. But it's the same. We still have this idea of data independence. Okay, so let's come back to tables. What are the takeaway concepts on a very, very high level? Well, you will see it's super simple. It's actually the goal that it's simple. That's why it's so popular. So first, in the relational model, we have the concept of a table. A table, we'll see that occasionally, especially in NoSQL products, it's called a collection. Instead of saying it's a table, we say it's a collection. Why? Because a table is just a collection of rows, right? This table here is a collection of these 4 rows, right? 1, 2, 3, 4. So we can call it a table or a collection. Next, we have the concept of row. So a row is basically one horizontal slice right there. You will find it under many, many, many different names. You will find it often called a tuple, a record, a document. That's for NoSQL stores. We like to call that a document. It would be a flat one, but I'll come back to that. An entity in the entity relationship model, even though a relationship could also be a record in a special table. An item, that's also a word that we will use for that. And this is my favorite, a business object. I figured out that the business people, this is why they call it. It's a business object. And yeah, everybody understands what that means, right? It's a business object. So this is one row of the table. So you see now we can already say a table is a collection of rows. Next, if you take a vertical slice instead of a horizontal slice, you get what's called an attribute. And of course, there's plenty of other synonyms: colon, field, property, key, and so on. So colon makes sense for a table. Field, property, key, again, that's more in NoSQL databases, as we will see later. But we can use all of that. So table, row, attributes. The notion of a primary key is also important. What is a primary key? It's a column that is special. It's a column that is special because it identifies the row. For example, a list of people, what would be a natural primary key in Switzerland? Probably your AHFA number, right? It's used at many places. Social security number in the US and so on and so on. That would be the primary key of a table of people, right? So again, it's a column that acts as a unique identifier for the rest of the data. It can also be several columns that together, like you could imagine also first plus middle plus last name, could also identify a person, right? Even though, of course, in the real world, it doesn't always work. You can have several people with the same, right? Any questions so far? Makes sense? Okay. I'm really oversimplifying here, right? This is almost trivial. We'll see, I'll show you a bit the formal aspect of it, but it's to make sure that even people who never saw SQL or tables, they understand what's going on, right? So now that we have defined tables as collections of tuples or collection of records, we can start manipulating tables. So the sort of things that we can do with them is called the relational algebra. Why is it called relational? It's because when you have a table like that, that's made in that case of 1, 2, 3, 4, 5, 6 rows and 3 columns, you can equivalently see this as a mathematical relation over, in that case, 3 domains. What does it mean? So I'm going to get a bit formal here because I know some of you will understand the math. You take the Cartesian product of the 3 domains. So D1 is the set of all values you can have here, D2 here, and D3 here. If you take the Cartesian product, you have every possible combination. There's no information in there at all, right? Because it's just a Cartesian product. The real information is when you take a subset of that Cartesian product. The subset of the Cartesian product is going to be the list of your records. The Cartesian product would be all possible records, right? And the actual relation is a subset of the Cartesian product, and a subset of the Cartesian product, this is what mathematicians call a relation. Right? So this is the reason why it's actually called a relational table. Right? However, this is the definition you find in many textbooks. It has a few drawbacks when you define a table in a relation in that way. The first drawback is that mathematically, a relation has an order, D1, D2, D3. There is a first, a second, and a third entry in each tuple. That's not quite right because in databases, we don't care about the order of the columns, right? If you have a table of people with first and then last name and birth date, it doesn't matter if you change the order of the columns. Like you have last name, birth date, first name, still the same data. So mathematically, it's not quite right because, right, the order right here is important. And then you basically need to kind of disentangle it saying, yes, it's like this, but actually the order is not that important and blah, blah, blah. So there's a better way that I think is also forward compatible with big data is to say that we should view a table as first a set of attributes right there. This in classical databases, last, first, and country. It's the names of our columns. And then to define what's called the extension of the table, the actual data, as a set of tuples. This is a tuple, this is a tuple, this is a tuple. There's 6 tuples in there, 6 records, and every tuple associates a column with a value. First with Albert, country with CH. So you could represent it that way. This is one tuple. This is the one, actually there's more data than in here, but basically if you take the first one, this is an example of one tuple, one row of the table with here the 4 columns, and here 4 values that you have for this specific tuple. this is in fact what's called a function, or more exactly a partial function, that associates strings, the actual attributes, to values. Of course, you're computer scientists, so that's just a map. It's an associative array, right? It's much simpler. So this is a map. So what is a relational table is basically a set of maps, right? It's a set of maps, and the maps these strings right there to values, right? So of course, database people never draw it in that way. This is how they draw it, right? You think of it as a table like that. And again, since it's a map, in a map, the order of the keys doesn't matter. So you see, mathematically, it's more correct to do it that way. So this is one record, one tuple, which is a map from strings to values. Okay, now you can try to paste together multiple tuples, multiple records, and get a table. Here's an intuition of when that works and when that doesn't work. Here, we have 3 tuples. Can we paste that together as a single table? Checking the time to make sure. Oh, still have 8 minutes. So we have these 3 tuples. Can we assemble that into a unique table? Who thinks yes? Yeah. Why? Exactly. They have the same attributes, the same 4 attributes. This is called relational integrity, right? So we can paste them together like this, right? So this is why you can define a relational table as a set of maps, and a set of maps that have some constraints. One of them is that all of the maps have the same keys, right? And then you can do that. That's relational integrity. This is when it's broken. Here we have 3 maps, but this is a bit broken because here you see the second map doesn't have a name, the third one doesn't have a value, a Boolean for physicists, and here there is a country and so on. So it's a bit of a mess here. It breaks relational integrity. This is not a table because we don't have the same values for every column. Now, okay, you could hit that with a hammer and turn it into a table, right? You can pretend like this is null, this is null, this is null, right? You could always do that, right? But technically, something's broken, right? It's a bit messy. Okay. Second, a second rule in order to get a table is that the values that you have in your table must be what is called atomic. Atomic, the etymology of the word means you cannot break it down into further pieces, right? So this is an example of a relational table that, as you can see, only have atomic values. So many of you can already know it's also called a scalar value in some systems and so on, of have an intuition of what that is. It's a string, it's a date, it's an integer, it's a Boolean, and so on and so on. I think the best way for you to understand what that means is to give you a counterexample. This is a counterexample of atomic integrity. Why? Because I have a table in a table. This is not allowed. You cannot do that. You cannot nest tables in tables, at least in the original relational algebra. Think of the Inception movie, a dream in 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 a dream. It's exactly the same thing, a table in a table in a table in a table. You cannot do that. If you want the atomic integrity, then you need to exclude any substructures in there, no tables. Anything that is structured is not allowed. It can only be simple values, right? And the third constraint we have is also to keep things tidy, is that we have a few rules on the domain of the columns. For example, here we must have strings. Here we have a string. Here it's a Boolean, meaning true or false, either true or false. And here we want an integer. So this means, of course, that you assign some types or domains to each column in order to restrict what there is in there. So these are called the domains in the relational databases. And a counterexample would be this, 0. Of course, you could argue, okay, 0, we can interpret it as false. Yes, but it's still messy, right? So here, this is not a Boolean, technically, it's an integer. And here, you could, of course, clean it. This is what data cleaning is about, right? You could still parse it as 42 and make it an integer, but technically here, it's just a string, right? So here, it's broken. This is not okay, this is not okay. So the domain integrity is broken. So 3 simple rules. Relational integrity, all the tuples have the same attributes. Atomic integrity, you cannot have a table in a table in a table in a table. And third rule, you must have domains specified for every attribute, and all the values in each column must be in the specified domain. When you do that, with this simple Venn diagram, if you have a table defined as a set of maps, a set of associative arrays, plus these three constraints, relational integrity, domain integrity, atomic integrity, then at the intersection of the three, you get the beautiful and magical world of relational tables, the relational algebra, and SQL. This is what we are brushing up today and tomorrow, right? Why are we doing it that way, and why do I like to tell things that way? Because in order to go to big data, it's super simple. We just throw away the constraints. So in big data, in this course, we are going to throw that away. We don't even care if there's domain integrity. We're going to throw that away. Yes, we'll have tables in tables. And we are going to throw that away, meaning yes, we'll allow if there's extra columns or missing columns, right? This is what makes big data actually interesting. But again, this week, we are going to just do a bit of brush up in this area right there before we venture outside of this and discover the larger world, right? Okay, so just SQL for now. I'm thinking we have 3 more minutes. So maybe I'll stay high level. I'll make sure that I don't do anything scary just at the end of the lecture. So I'm just going to repeat this notion of relational algebra. What is it? It's a set of mathematical operators that manipulate tables. You know, just like addition, you can manipulate numbers with addition. 2 plus 2 gives you 4, right? This is the same. Plus gives you an operator that manipulates integers, right? We can do the same with tables, except that instead of integers, we have tables. And there is the relational algebra that consumes and produces tables all over the place. SQL is just a language that allows you to write down a program that manipulates tables in that way. So in a way, it's a table calculator. It's like a calculator, but instead of numbers, you have tables. That's what it is. All right, so this will keep for tomorrow because I will tell you, of course, the sort of things that you can do with tables, but I'll do it tomorrow. All right, so I think this is enough for today. I hope it was a good appetizer for you. So thank you very much for attending. I'll see you tomorrow in the main building at 9 or on Zoom, and we'll take it from there. All right, so see you. Thank you very much. Goodbye.